In this video, we're going to learn about the limit comparison test. The limit comparison test is kind of similar to direct comparison because we get to pick a series, but here's what it says. So the series we're given is Bn, and the series that we pick is An. And if we take the quotient of those two and the limit as n approaches infinity, if that gives us a positive and finite number, then those two series, An and Bn, either both converge or both diverge. So they both do the same thing. Only if we get something that's not 0 and not infinity and not negative. The tips for choosing the series with An are fairly similar to how you would choose it for the direct comparison test. There are just a couple little variations on this. So the first one, choose a simple version of the series that you're given. That is covered pretty thoroughly in the direct comparison video, so if you need a reminder, feel free to watch that one. The second tip, you want to choose something that easily combines with the part of the series that you're given when you make a quotient out of the two of them, or when you find the quotient of the two. So, for instance, if you have something with just polynomials in it, you don't want to pick something that's got maybe a natural log. Pick something that looks similar and that will make your life easier when you go to divide them. So here's an example where we have n over n squared plus 1. And 1 over n, I have an n here and an n here, so when I go to divide these, I have to do my keep, change, flip thing. But it's easy to combine them because n times n is just n squared, so I'm not adding any extra terms, really. I'm just changing the power on one of these things. And now it's really nice because I have an n squared over n squared, so that's another benefit. And it is hard to choose An sometimes. It's sort of an art to do it a little bit. You just have to practice, and you can always, if you pick something and you can't get it to work nicely, then pick something else. That's fine too. You don't the first series you choose doesn't have to be the one that you end up using. Another thing, you want to make sure that you're choosing something that does not give an infinite or a 0 limit when you have that quotient. So for instance, the first one's in red because it's wrong. If we have the series n squared plus 5n, and we take n, it seems like that would be okay, but now when I do my quotient of those two, and I take the limit of that, as I go towards infinity, I can kind of, n goes into both of those, so that simplifies to n plus 5, which gives me infinity. But if I have an infinite limit, then I can't use the limit comparison test. So, same series, but maybe this time I pick n squared, because now, as n goes towards infinity, the 5n isn't important, so I get n squared over n squared, which is 1, and it's positive and finite. So that's probably a better choice for An. And the last tip, this is the same as direct comparison test. Make sure you choose something that you can easily find the convergence of. So back to the same series we used in the last example. If we have n squared plus 5n, then we can pick the infinite series n squared because we saw what happens when we take the limit. The limit is equal to 1. But we can also easily find the divergence or the convergence of this because it's just a p series, so I have 1 over n to the negative 2 if I rewrite n squared. And negative 2 is less than or equal to 1, so that means by the p series test it diverges. So here's an example with the whole thing. We're going to use the limit comparison test to determine the convergence of this series, 2n plus 1 over the quantity n plus 1 squared. First thing I did, n plus 1 squared is maybe a little bit hard to think about, so I just FOILed it out, n squared plus 2n plus 1. And I'm going to go with the first tip of picking something simple that looks like my series. So basically I'm ignoring all the small terms, and I'm just going to use the first one from the top and the first one from the bottom, or the biggest one from the top and bottom, which gives me 2n over n squared, and I can cancel out an n, so I get 2 over n, which, to make it even simpler, looks like 1 over n. So that's going to be what I pick for my An. Whatever you choose for An goes on the bottom of the quotient. Whatever you're given in your problem goes on the top, so it's more complicated on top and simple on the bottom. Alright, and we want to find the limit as n approaches infinity, but this looks kind of insane right now, so we're going to simplify that a little bit. So remember, when you're dividing by a fraction, you could also multiply by its reciprocal, which means the top part, the series that I'm given, stays the same, and then I multiply by 1 over n, because really I was dividing by 1 over n. So now I multiply by n over 1. And there's different ways you can do this, but I just distribute the n in, so I get 2n squared plus n over the bottom that doesn't change, n squared plus 2n plus 1. And we're taking the limit as n approaches infinity, which means I can ignore all of the small terms, and I end up with 2n squared over n squared, which is just 2. And the nice thing about 2 is that it's positive and it's not infinity, so that means that the two series that I started with, this one and this one, they either both have to converge or they both diverge. So now the series that I chose, 1 over n, that's the harmonic series, so it diverges. Also by the p-series test, because p equals 1, which is less than or equal to 1, so it diverges. And because the one on the bottom diverges, and because this was positive and not infinity, that means that the series that I was given in my problem also diverges. Alright, so here's one for you to try. Use the limit comparison test to determine the convergence of the series 1 over 2 to the n minus 1. Pause the video here, and when you're ready, we'll look at the solution. Alright, here we go. Our series is the infinite series of 1 over n, 2 to the n plus 1, which sort of looks like, if we ignore the plus 1, it looks like 1 over 2 to the n, which is great. That's a geometric series because really it's the same thing as 1/2 to the n power. So r is equal to 1/2, which is less than 1, and so for a geometric series, if r is less than 1, it converges. So this series that I'm choosing converges. And then I do my limit comparison test, so I have the limit as n approaches infinity of the one that I'm given, 1 over n, 2 to the n plus 1, over the one that I choose. So given on top, chose on the bottom. And then again, I've got fraction over fraction, so it's hard to work with, so I do my keep, change, flip thing. So I keep the numerator, and then I multiply by the reciprocal of the denominator. And so that gives me 2 to the n over 2 to the n plus 1. And then as n approaches infinity, I can ignore this plus 1, so really I get 2 to the n over 2 to the n as n approaches infinity, which is just equal to 1. And 1 is positive and not infinity, so that means that whatever this series does, the other series also does. And I know that this one converges, so that means that this one also has to converge. And that's it for the limit comparison test. Ask questions if you've got them.